Hey everyone, and welcome to this Forge College Explainer. I'm absolutely thrilled to have you here today. All right, let's just dive right into it, shall we? Today, we're basically putting on our Master Architect hard hats. We're going to take our Solidity smart contract storage and completely evolve it. We're moving from basic single-drawer filing cabinets into fully fledged complex data centers. And the blueprint for today's build? Using mappings with Structs. Now, if you look at the contrast between where we were and where we're heading, it's pretty massive. In our previous lesson, Mapping Fundamentals in Solidity, we learned how to map IDs to single primitive values, right? Think of it kind of like a simple coat check. One ticket gets you exactly one coat. But in the real world of decentralized apps, things just aren't always that simple. So today, we're drafting a much more sophisticated blueprint. We're mapping IDs to custom grouped struct records, meaning one single ID is now going to unlock an entire profile of interconnected data. So here's our game plan for today. We'll start with the storage blueprint evolution. Then we'll draft our record struct, wire up the add and read functions, cover safe in-place state updates, verify the assembly, and then wrap things up with a schematics review. Let's break some ground. All right, Section 1, the storage blueprint evolution. Evolving storage. Real-world Web3 applications require unified, complex data structures, not scattered data slots. Let's see how we actually build that. Moving on to Section 2, drafting the record struct, custom data containers. You can basically think of a struct in Solidity as your completely customizable container. You define exactly what goes inside the thing. And here is our exact blueprint, our record struct. Look closely at these fields and, their engineering realities. We've got a name, which is a string. Now, because strings can literally be any length, they're dynamic. They actually take up separate storage slots, so our mapping really just stores a pointer to where that string data lives. Then we have balance as a uint 256, which fits perfectly, like a glove, into a single 256-bit slot. Next is owner as an address and active as a boolean. And because of how Solidity optimizes under the hood, smaller types like booleans and addresses can often be efficiently packed right into the exact same storage slot. So this isn't just neat organization, folks. This is highly gas-efficient engineering. So you might be wondering, how do we actually connect our simple numeric ID to this beautiful new container? Well, we do it with this highly elegant line of syntax. We write mapping, open parentheses, uint 256 pointing to record, and we'll just call it private records. Boom. We are taking a standard uint 256 ID, which is our key, and pointing it directly at our newly drafted complex record structure. Just like that, ID number 1 unlocks a name, a balance, an owner, and an active status, all at the exact same time. Section 3, wiring, add, and read. Data lifecycle operations. Let's take a look at the actual lifecycle of our data here. Step 1 in our data lifecycle is adding a record via full assignment. That means slotting all the fields into memory all at once. The name, balance, caller address, and active status, and putting it right into our mapping. Then step 2, we retrieve the record using a view function. And finally, step 3, we verify the return tuple. See, we don't just return the raw struct directly. Instead, we return a tuple of its components. And we do this to ensure off-chain apps, like your dApps front end, can easily read and parse our stored data using standard ABI compatibility. Okay, wait, I need to pause right here for a second because I have to warn you about a classic developer trap. What actually happens if you try to read a record for an ID that doesn't exist yet? Well, let me tell you, Solidity is absolutely not going to hold your hand and throw a nice, helpful missing key error. Oh no, it is just going to hand you a zeroed struct. That literally means all numeric values are 0, booleans are false, and strings are totally empty. So you might look at that retrieved data and just scratch your head going, wait, did Alice really have a 0 balance? Or does Alice just not exist in the system at all? This exact ambiguity, and honestly the massive headache it causes, is exactly why our struct blueprint includes that active Boolean flag. It is our definitive, undeniable existence signal. All right, Section 4, safe in-place state updates, in-place modifications. Now, I really want you to burn this exact rule into your brain. Assigning record memory creates a temporary copy. Always use record storage for in-place updates. I cannot stress this enough. This is probably the most common and frankly disastrous trap for new smart contract developers. If you declare your struct variable with the memory keyword, you are just downloading a temporary, fleeting copy of the data. You can update that copy's balance all day long, but the actual on-chain state, it won't change one single bit. It's exactly like editing a photo on your phone and expecting the giant billboard downtown to just magically update. It doesn't work that way. Let's actually view this comparison side by side to really drive the point home. On the left, we have record storage R. This gives you a direct, live pointer to the on-chain state. When you update r.balance, you are directly mutating the blockchain. It's highly gas efficient because you only write to the specific storage slot that changed, leaving absolutely everything else untouched. But over on the right, we have record memory R. Here, you spend precious gas copying the entire struct into memory, and any changes you make just evaporate into thin air the moment the function call ends. It's a total waste of gas and logic. So the absolute crucial point to remember here is this: storage is load-bearing. Always, always use it for updates. Section 5. Verifying the assembly. Manual testing. So here is our verification sequence, which, by the way, you can easily run step-by-step on a local virtual machine like Remix. First up, we add Alice's record with a starting balance of 100. Next, we call our getRecord function to verify that yes, the tuple returns Alice, her balance is indeed 100, and she is correctly recorded as the owner. Third, we use our storage pointer to update her balance safely to 250. We check it again, and boom, only the balance changed to 250. Her name and active status perfectly pristine. And finally, we absolutely must test non-owner access. So we switch our local account and try to maliciously touch Alice's balance. Which brings up a really vital question. What actually happens if account B tries to update Alice's balance? Well, it's kind of funny to think about, because without access control, it would be absolute chaos, right? Everyone could just overwrite everyone else's data. But thankfully, since we're smart architects, we added a simple require statement checking that the message.sender is equal to the record's owner. So, when account B tries to pull this nonsense, our contract correctly rejects the transaction, reverting it entirely with a caller not owner error. Rejected. No state change occurs at all, and our data remains completely safe. All right, final section, section 6, schematics review. Review and next steps. Okay, to keep your on-chain data both secure from accidental overwrites and highly gas efficient, here are the core principles you need to live by. Number 1. Mappings return zeroed structs for missing keys, so please do not get fooled by ghost data. Number 2. Because of that first rule, always include explicit active flags in your structs to definitively prove a record actually exists. And number 3. Rely heavily on storage references, that magical storage keyword, to safely mutate individual fields in place without overwriting or copying the entire struct. Now, as we finish up here, I'm going to leave you with a final provocative question to ponder. We now know exactly how to map a simple numeric ID to a complex multi-field record. But how do we safely index these structured records with even more complex composite keys? Say mapping an address and a token ID together to find a specific struct. Well, that is exactly what we're going to tackle in our upcoming nested mappings and key hashing lesson. To continue this Web3 architecture journey and to learn more about this subject and just so many others, I highly encourage you to visit forge.college. This explainer was made by Forge College, and we honestly cannot wait to see what you build next. Keep learning, stay curious, and I will see you in the next one.